Thank you. It's a pleasure to be back here. I was in Dubai earlier this year for the World Government Summit as well as the year before. So I see a lot of activities in the area in the space of AI, and so much is moving fast. So it's great to be back here. So today I'll talk about what it means to be the Trinity of AI. Right? So there's not just single ingredient that makes AI successful, but three major components that I call the Trinity. And that's what has led to this so-called deep learning revolution. And the question is, where do we go from here and what are the next steps? So that would be the goal of this talk. So as I said, the Trinity incorporates data, algorithms, and the compute. These are the three important facets that need to come together. So why is data so important? Right? Because, AI has been around for a long time. There has been excitement about AI for a long time. But what made the last few years very special was this large availability of data. The internet made it possible for us to accumulate data, accumulate images, text, now videos, and all kinds of rich data, and make available data sets to the researchers to see what algorithms work well. So the deep learning revolution started with the creation of ImageNet. Dr. Fei-Fei Li and her collaborators decided that we needed a much bigger data set on which we could try algorithms, and that was the only way to take AI forward. And that was visionary to come up with that insight. Right? So it started with the creation of the ImageNet challenge. And once this large data set was available, the second component was the algorithms. So deep learning consists of neural networks that has many layers of processing. And the question is, why is this better than some of the other methods that were very much in fashion before ImageNet was created? And we'll see that this flexibility of neural networks was critical in order to incorporate all the data features that's available in this large data set. And the third important component that we don't always think about when we think of AI, we think of mainly the algorithms to begin with. We may then think of the data, right? But the third facet of compute infrastructure is equally, if not more important. And the NVIDIA GPUs have been at the forefront of this deep learning revolution. Because once you have large data sets and large models, you need to compute this, right? You need to be able to process all this. And for this, you need highly parallelized and efficient computational platforms. And that's what GPUs offer. And all this coming together has made this deep learning revolution happen. So that's the summary of where we are today. Let's dive a bit more into these details and then look at where do we head next from here. So to begin with, one of the canonical tasks for deep learning has been computer vision, and in particular, understanding what's in an image. So for us humans, this is so straightforward, right? I show you the image, you can already say so much about this. But for machines, this is extremely challenging. And that's because there can be so much variation going from one image to the next. The shape of the swimming pool can change when you go to another image. It may not be with a house, it may be with, a hotel or a big building, right? So there can be all these variations that we humans implicitly understand and can still recognize, even with all the variations, but it's much harder for the machine to do that. And that's when people try to initially come up with rules, right? They try to write down what makes a swimming pool and try to tell the machine it's not scalable. Because there are just so many variations, we can't just write them down into rules. And that's why, this modern machine learning instead says, let's learn from data itself rather than trying to hand engineer features or write down rules. And that's the premise of deep learning. And that's where, this creation of ImageNet dataset for the first time contained millions of images, about 14 million images, and also lots of categories, about 1,000 categories of them. And this was orders of magnitude bigger than any other dataset before this, right? So this quantum jump in the size of data made a huge difference in being able to have good accuracy. And even within each category, you want to look at what are all different kinds of variations you can see. For instance, if you look at the category of fish, right, there is like fish of different colors and different angles, but also like humans carrying fish, right? I mean, if you take images from the internet, it's inevitable that it'll have a human bias. So, so we'll always have this bias in data based on what images get uploaded to the internet or whichever source we collect at. And so that's something to keep in mind, that if we are taking these data sets from the public domain or from a large domain without much control, there is some inevitable bias introduced because of that. But that's something to keep in mind for more nuanced analysis. So that's the idea, that you have these large data set to work on. Then the next facet was the algorithms, right? So what are efficient algorithms on which we can apply these large data sets on? And so that's where this notion of deep learning or neural networks with many layers became very popular. So the main idea is you take the input image, you send it through processing over all these layers. And at the end of it, you get an answer. The answer is thought of as a probability, right? So if the model's trained well, you would like it to say that this is most likely a dog. But, it could be a cat with some small likelihood, right? Because cats and dogs have similar characteristics in some ways, so there is still some potential for that to be the cat. So that's the idea, that you send this through many layers of processing before you make the final decision about what's in the image. So why is it important to have these layers of processing? So we don't completely understand, but we have some intuitions. And the intuitions is one of compositionality. So the idea is, if you look at just the first layer of the neural network and visualize it, what you end up seeing are filters that can process very simple shapes. So think of lines at different angles, and that's what you can process in the first layer. But then you go to higher layers and you end up combining these simple shapes into more complex ones. Right? So it's learning how to combine these in a way that corresponds to the images in the data set. So it's learning these filters or weights in terms of what it should be in every layer and how you should combine them. And so that's the idea of these multiple layers of processing that's very critical. And that's been the deep learning revolution, to say you can't just do this with one layer or a few layers. You may end up needing lots of layers of processing, and also models with potentially a large number of parameters. Some of these ImageNet models could have even up to 1 billion set of parameters or billion set of operations for each image. Right? So these are now very large data sets, large models. And that's why, in order to be able to process them, we need highly efficient computation. And that's been given by the GPUs, or graphics processing units, from NVIDIA. So why is this important? And why am I talking about graphics? Right? Because even though NVIDIA originally used this for processing graphics, the same underlying linear algebra and matrix computations also underlies deep learning. Those layers of computation that involves matrix computations can be incorporated into this GPU operations. And that has been critical for speeding up and scaling these large models. And what this graph is saying is that the Moore's law is pretty much dead now, meaning we can't just expect single-threaded computational abilities to increase at an exponential rate. And then that's why we need to go to parallelism, and that's the only way we can keep improving our computational abilities. And so this has been critical for being able to train these large deep learning models. And so when all these three came together over the last few years, right, there was rapid progress. Because I think, this is where there was this big shift, right, in the error rate. So this is measuring how much error you make on the ImageNet dataset. And what you see is year after year that kept improving once people realized that you can use neural networks and get very high rates of accuracy. And ultimately, here, it even surpassed human abilities. Of course, you may wonder, now is this better than the human? Can it recognize images better than the human? That's not true, right? What it's saying is it got better on this data set, but this data set is still tiny compared to all possible images we would see in the natural world. And so what this is suggesting is we've now reached the limits of this data set, and we need now a much bigger data set to get the next quantum leap in accuracy as well as other abilities of being able to understand images very well. And so that's another challenge, that it seems that no matter how big a data set we collect, we always need more. Right? And so that's another challenge now on, can we design better algorithms to work with the data we have rather than asking for more? And so that's an open problem. So that's the idea. We are here so far by, bringing together the data, algorithms, and the compute infrastructure. And the question is, where do we go from here? And what are potential applications where we can make leaps and get very good performance? And so what I want to now cover is, where do we go in terms of taking AI and building it into a body? So far, when you think of AI, it's just the mind and not anything to do with a physical body, right? Whereas if you think of robotics, that deals with how to be able to interact in the real world and do many different tasks. But we want to make that intelligent, and that's what I call the embodied intelligence, the mind and the body coming together. And if we want to accomplish this, can we take this principle of Trinity further and ask, what does it take to have embodied intelligence? What kind of data sets would we need? What kind of algorithms would we need? What kind of compute abilities would we need? And why is this the next big challenge? Right? So if you think of applications, there are just so many there. Robotics and AI coming together can now completely change how we think of doing things. For instance, in manufacturing and logistics, currently there is robot manufacturing, but it's all pre-programmed. Trying to change the program is quite challenging. Trying to maintain it is also quite challenging. If you could have intelligence built into it, you can make all these processes so much more seamless. Another exciting area is healthcare. There are so many areas of healthcare where AI can make a huge difference, all the way from medical imaging, where if we can automate and or have human in the loop to understand all kinds of different scans efficiently and have early detection of tumors, and combine that with health records and genetic information and all kinds of other data in terms of being able to predict diseases efficiently, we can make big leaps. So there's a lot of potential for AI to help us detect diseases better, predict different conditions, and also make healthcare overall cost-effective and efficient. And add to that, if you now bring in robotics, you can have now surgeries being performed much more accurately, as well as costs going down by huge leaps. Right. So what I show here is this robotic surgery platform from Intuitive Surgical. Currently, it's completely operated by the human. So meaning the human is remotely sitting there and operating this. And, but it's this machine that goes into the body and does the required tasks, right? So even though we call it robotic, it's really human operated now at the moment. And the question is, can we now, get to more intelligence and towards automation in this task? And indeed, this would be one of the most challenging tasks for embodied intelligence. But if we can accomplish it, that can be so exciting and so impactful. So given that there are all these different applications, at Caltech, we came up with what we call moonshots. It's because instead of trying to go to every sector and every specific application of robotics, we asked ourselves, how can we divide different kind of tasks that robots can do? And then we can go into the scientific problems of what does it take to do these tasks. And so that's where we came up with these notions of, there can be robots that are explorers. They can be guardians. They can be transformers, transporters, and partners. So we believe this covers all the different applications that you can think of for embodied intelligence. So what are explorers? Explorers are robots that are autonomous and that can explore either on Earth or other parts of the solar system and go on many different kind of terrain surfaces, and they have different goals in terms of being able to collect new useful information. We have the Mars rover, we have so many different examples of such explorers, right? And the question is, can we build better intuitions into them, better intelligence into them, to make them efficient and be able to also deal with harsh conditions when there's no human available to go rescue them or be able to, intervene and help them. Right? In such situations where complete autonomy is needed, it's extremely challenging for these robots to navigate, but also decide what's interesting. Right? So if you're an explorer, you have to cut through all the noise and all the usual features and go to something that can be truly a new discovery. For instance, on Mars, if you want to find life, we want to look for very specific patterns rather than just go explore any rock. Right? So it's important to have those notions of intuitions for being a good explorer. And so that's what we call it as moonshot number 1 on how we can build good explorers. And at Caltech, we have this goal that there is this bipedal robot in Aaron Ames' lab that's called Cassie. We named it Cassie. We also have drones in Sunjo's lab. And we have all kinds of other robots as well. And the question is, can we have them all coordinate and can they walk autonomously different terrains? In fact, we wanted to ultimately go walk the coastal trail in California and span that. That's a 10-year goal to head for. And so that's an exciting goal for us to try and accomplish. So that's the first one. The second one of guardians is also really critical if you think of applications that can mean life or death. So these are protecting humans and saving lives in many disastrous situations. The fires in California is unfortunately a recurring theme every year. And can we be very having these robots go into these threatening situations and be able to make quick decisions on how you can save the most number of lives and how you should plan for that. Future, then it can be not just one human-operated drone, but drones being autonomous and also being able to coordinate with each other in many different ways. We have this project called Flying Ambulance at Caltech, where the ultimate goal is there'll be autonomous ambulances that'll be flying and looking for casualties in, say, areas of disaster or war, and be able to lift, the humans who need help in such situations. So this is, again, involving a number of different challenges to be able to handle them well. The third one is what I call transformers. The transformers are robots that, are swarming together. There's a group of them, and they are either constructing something or transforming existing spaces. So you can think of it as, if you go to an asteroid or extraplanetary systems, if you can now go and construct, different aspects that can go and further explore, then you need also these aspects that it's not just fixed structures, but you're also transforming and potentially creating new robots. And lots of challenges here to be able to do well. I mean, some examples are like space telescopes. The Hubble telescope was assembled in space. You cannot just have this big telescope be taken from Earth. So in those situations, you need to be able to have robots that can coordinate and accomplish this task well. The next one is our transporters. So these are indeed our dream, So that is the Jetsons, where we are all zooming in air, and that's how in that cartoon people travel. We aren't there, but that's our hope. If we can beat all the traffic and just go use the 3 dimensions in more effective ways, that would be amazing. And indeed, there are a lot of challenges starting from the energy efficiency. I mean, indeed, climate change is real and a huge concern. If you have to have everybody take to the air, we have to come up with ways to make that energy efficient. And we have to have ways for the coordination of all these different flying bots. And also we have to think about safety, So if we have lots of these, even if the chance of failure is small, if you have millions of them, the whole equation changes. So you need much stronger safety requirements, and that's why this is so challenging. So it's not just a matter of putting an AI into the systems and, okay, it's fine, You have to think about safety, stability, all these other challenges that come with it, and that's why it's so challenging. And the last one are the partners. So these are either part of the human body or interact with us in so many different ways. For instance, they can be exoskeletons. Somebody who's lost a limb, unfortunately, or having all kinds of physical, conditions could benefit from, having robotic systems that can help get back their mobility, So as the population ages, this is so critical if we can keep them mobile and if we can keep them active. And there's a lot of work on exoskeletons at Caltech on being able to have these systems have some intelligence in being able to assess what the human wants from it, How much should you move? What should be the gait? Can you learn that and be able to work with the human together? Chatbots are another great example. If you can recognize what the human wants and do that in a very interactive manner, that can accomplish so many tasks. If you look at Siri or Alexa today, you can just do like one at a time. You can say, what's the weather? It says, what's the weather? Then if you say, take me to the airport, it doesn't kind of really recognize the context and the states, So you can't have a continuing conversation. It's only like a one-time thing. And so there are lots of challenges if you want these bots to become more intelligent and be able to carry on different dialogues and have maintaining different contexts through the system. And so I think these are the different challenges you can think of, And many applications will fall into one or many of these slots here. We have the explorers, guardians, transformers, transporters, and partners. And like I described, there are so many challenges to make them work in real applications. And even if we like think of mostly toy-like ones, it quickly gets very challenging because what we are asking of them is a lot. Right? We want them to go explore on their own. We want them to make decisions on how to save human lives in important situations. We want them to coordinate and build structures. We want them to be safe transporters. And we want them to partner with us in so many ways. And so that's where I think thinking of these as moonshots helps us anchor our research in many different directions. So where are we today? Okay, so we have all these exciting moonshots. We want to get to the moon. But where are we today? So the Boston Dynamics Atlas robot is perhaps one of the most sophisticated robots we have today, right? And then we have our best friend. If we think about how the two compare today, the Boston Dynamics robot can, turn, it can do an impressive backflip, whereas the dog may not always succeed and can fumble. So you have, on one hand, a precise programmed robot that can do one thing, and it can mostly do that well. But you have a dog that doesn't always do well, but then it's able to learn, right? It's able to understand us to a large extent. It's able to take commands, and it's able to learn different skills. And that's why the dog is so much more intelligent than anything we can do today, right? So that would be a good thing to aim for if we can create that in the robot. And so that's the challenge, that our current robotics have almost no intelligence into them. And it's all pre-programmed and it's all, specified by the human. But the hope is if we can make it data-driven and have it learn from data and be adaptive based on that, then we can aim towards these moonshots that I described. So that's where I would again go back to the Trinity, right? So if we want to achieve this embodied intelligence, what is now the Trinity equation we need to come up with? What kind of data set should we have? What kind of algorithm should we design? And what's the computational framework for realizing this? So for robotics, the data gets to be much more complex than what we see in these AI applications that I showed before, right? Because it can be highly multimodal. You can have videos, you can have sensors, you can have sound, you can have text. The robot should be able to recognize so many different forms of data. So that's why I call it multimodal, because it has these different modalities and we need to be able to process that. So how do we express and process all this data? So that's where there is this notion of tensors that I work on that can be very efficient in processing such multimodal data. So what's a tensor? A tensor is a matrix in more dimensions, right? So if you've done some basic linear algebra, you would know that a point is just zero-dimensional, right? So it has no dimensions. Whereas a vector is one-dimensional, meaning it's a line with a direction and a length. And a matrix is two dimensions. It has rows and columns. And now if you want to express data that's more than just rows and columns, you need tensors, which can have many different directions. And you can think of this as a multi-dimensional array, but you can also think of doing operations on this. Just as we can multiply two different matrices and come up with a new matrix, similarly, you can think of operating on tensors and coming up with new tensors, right? And that's where this algebra of how we compute over tensors is what I look into and what I want to design good algorithms for. And that's really critical for this multimodal data. And so when you have such multimodal data, you have tensors that are coming into different layers of your neural network. And so we can ask ourselves, how do we design good primitives for different layers of processing? In one of the projects, what we did was to ask, what can tensors do better that matrices cannot? right? The main intuition is, if you have this high dimensional tensor and you want to project this. So in this simple example, this cube is getting projected onto this wall. You lose information, right? It just doesn't capture the same information if you project it to lower dimensions. And that's why, we designed networks where instead of using matrices to process information in the layers of a neural network, we extended that to have tensors in all the layers. I'll skip some of the details, but the idea is you can make these computations efficient, and you can also reduce the number of parameters in these layers. So roughly what this is doing is taking the earlier matrix operations in the layers and coming up with much more compact layers of tensor processing. And with this, what you can have is nearly the same accuracy with a large amount of space saving, meaning you can come up with networks with far fewer number of parameters, as much as 65% fewer number of parameters, and still be able to have good accuracy. So the idea is there are ways to take this data that is represented as tensors and still be able to process them as tensors across the layers of a network. And so we have a software called Tensorly where you can play with these different operations and design networks that go beyond the standard neural networks. And this is easy to use. There are lots of example Jupyter notebooks. This is in Python. You can do it with different deep learning frameworks. So that's the other aspect of, algorithm design these days. It has gotten a lot easier with the use of different deep learning frameworks. And so I welcome you to go and try this out. It's open source and it's available on the net. So that was the angle of taking data that is multimodal, representing it as tensors, and designing neural networks that can take in the processing of these tensors. So the next aspect is how do we also speed this up in hardware? So currently, we have what's known as BLAS, or basic linear algebra subroutines. So these are primitives that are designed in GPUs to make matrix multiplication extremely fast, right? Because everything that underlies these neural networks at the moment are matrix multiplications. So this is the Pascal GPU, that's the previous generation, and the Volta GPU is the latest generation. And what's happening now is you can see there's much more parallelism and hence much faster computation, right? So you can multiply these through matrices very quickly. And so these kind of primitives, once you speed them up, you can now also have neural network processing be sped up significantly because of such design. And so the next generation GPU algorithms would not only speed up matrix multiplications, but also tensor operations, right? So you take these now higher order operations and ask how to speed that up on GPUs. And so with that, you're also now getting the hardware gains along with small networks, right? So you're now representing data as tensors and having networks that are smaller and being able to process them efficiently. So all this Trinity is coming together to ask for the next generation, which go from matrices to higher dimensions and make these much more efficient. And so that was one way to scale up our operations, right? Because in robotics and in embodied intelligence, I talked about requiring more data, more computation, but with the use of tensors, we can still hope to scale that up. But there can be many other ways to also incorporate this. And one important consideration is if you're putting them on board onto these devices, you need fast computation on the actual device, right? For instance, there are delivery bots, there is aerial inspection. These are now, you can't expect them to be always connected to the cloud. You need to be able to do processing on board and be able to take in video and all kinds of rich media data and be able to process that. And that's where we have the new AGX platform where it's possible to do this high-speed, large-scale computations, and those applications are now within reach. And so this is the Jetson Xavier framework, and you have different levels of, again, size of the chip, the computational abilities, and different applications. So you can now not just rely on the cloud or any big cluster, you can also do efficient AI even on small devices, right? And that is a critical component if you want to have embodied intelligence. So the next aspect is, what are some other algorithms we can design for embodied intelligence and other next generation applications? Like I mentioned in the beginning, deep learning requires huge amounts of data. So when you're this data hungry, in many cases, you may just not get the gains of deep learning unless you can get the large data sets. So is this the only way, or can we do something else? It turns out you can do something else in many cases. Because why just go by data? Let's also build in different priors or prior knowledge we have about the domains. And when it comes to robotics, we know so much about the physics, right? We know Newton's laws of motion. We can encode that. We don't have to have AI learn that from data. And so these aspects of taking in traditional control and all the domain knowledge and fusing it with AI in interesting ways can lead to a lot of efficient algorithms. For instance, you can think of state estimation. So if you're a drone, you have to predict where you will go next, right? What kind of forces you will see and what you should be doing, how you should be controlling. And if you don't have a good model, you'll come up with a large error. So the challenge with drones is the aerodynamics is very hard to model. Right, so if you have wind, if you're near the ground, it's complex aerodynamics of many rotors together. So, and that's why you can't just write down as a model, you want to learn that from data. But on the other hand, the other aspects, if there's no wind, how the drone moves in ambient conditions, you can write that down with Newton's laws of motion. Right, so the idea is what you know already, you keep that, and then the unmodeled part, you can learn that from data. And that's what we did at Caltech in this drone project, where here we use data in the neural lander to learn to land more efficiently. And the baseline is not learning, right? And you can see that it was much more efficient and graceful in terms of the landing. So just to play one more application of that, you can also do very precise trajectory control. So you can be just a few centimeters off the ground and be able to do this circular movement we ask the drone to do. And here, if you're looking at like inspection or those kind of tasks, you may need to go very close to the ground. And we can now do that with the use of AI. So if you just had the standard drone controller, you wouldn't be able to do this. And so that's why just AI by itself wouldn't be able to do it. If you just use standard controller, you wouldn't be able to do it. But the two together, you can do this very efficiently. And so that's why we call this physics-infused learning, because you're infusing the prior knowledge of the physics and the deep learning from data together to get very efficient drone landing and drone flights. And the next step, what we have is being able to handle different kind of wind conditions. And that's where we have a unique wind testing facility at Caltech. These are about 1,300 fans here, and we can program and control what kind of winds we want to have. And so you can have precise safety testing with this equipment. We can collect all kinds of data. We can use AI algorithms to come up with guaranteed handling of wind conditions for the drones, right? So if we ultimately want drones to carry humans, it's so critical to be able to have environments like this where we can test different drones and make sure it can handle different conditions. And so this kind of physical equipment along with AI algorithms is so critical, right? Because we have to be able to generate interesting kinds of data, and we're able to do that at Caltech in this project. So what if you can't have a lot of real data, right? So in those cases, you can use simulations. And at NVIDIA, we have this platform called Isaac, where we can do a lot in simulation and then bring it to the real world. For instance, this is in NVIDIA Seattle lab, where there is a kitchen robot. So we'd like it to do different tasks in the kitchen, like place different objects, close and open drawers, and so on. So in order to be able to handle different kind of drawers, different kind of tasks, we can do this in simulation. For instance, we can generate different kind of cabinets and drawers, right? It need not be even just the one single style. And we can scale this up, and in simulation, you can try out many different strategies, many different kind of movements to go and open drawers. So the robot can learn very efficiently in simulation by trying out different strategies. And then we have to ask how to bring this to the real world, and that's where we have to design algorithms known as sim to real. So go from simulations to the real world. And this changes from application to application. If we have, simulations where, let's say the grasping, like those parameters are mostly okay except for a few changes, then you can go to the real world and calibrate it. If you're off by a little, you just learn that the algorithm in simulation cannot be completely trusted, right? But there's a lot of interesting challenges if the simulation is quite bad and quite different from the real world, right? So what do you do in those cases? Can you still use simulations effectively? I think these are open challenges for which we need new algorithms. And that's what makes it really exciting to be able to design for that. So this NVIDIA platform for robotic simulation will help us scale this up, right? Because if you can do this on GPUs and do it in parallel, you can try out so many different strategies, so many different environmental conditions. And the hope is once we take it to the real world, we can design what was that environmental condition and task we want to use on the real world. And a similar philosophy is also with the NVIDIA Drive platform, where ultimately the goal is autonomous driving, but then there is a platform for all kinds of drive applications. And, because one is about collecting data from the real vehicle, right? So we have these NVIDIA cars going out and collecting data. But then you also have the simulator where you can generate all kinds of interesting conditions. So currently we are testing what are the failure modes of the current autonomous cars, because every autonomous car today can fail in so many ways. So how do we generate challenging conditions for these autonomous cars? Right? And how do we test and make sure that they can handle different realistic conditions? You can only do this in simulation. No matter how much you drive in the real world, thankfully accidents are fairly rare. You may just never get all possible conditions of accidents, and you can only do that in simulation. And that's why we are very excited to have very high quality photorealistic simulations, as well as realistic physics and others incorporated into our simulation environment. And so with that, you can now train different kind of deep learning models. There's one for cars, for pedestrians, for lanes. So all these different models, how do you bring them together and how do you reason about uncertainty? Because, the AI also needs to know what it doesn't know, right? It's so critical for autonomous driving because then it can, tell the human to take over, because many of the fatal accidents, if you saw, with the Tesla car, for instance, that happened because the human was notified very late, right? They couldn't just jump in, or they were sleeping or having, just not enough attention. So how the human interacts with the AI is also quite critical in these applications. And we can test all this in a platform, and that's why it's important to think of the holistic picture, because you want to use the real data, but you also want to use the simulation in interesting ways. And I think bringing all this together and designing new algorithms is what excites me to be part of NVIDIA. Another aspect of thinking of algorithmic design is maybe everything you can't build simulations, right? Because building simulations also takes a lot of engineering resources, a lot of domain knowledge. So what if you only had data and not all of this resources? So in that case, we can think of generative models. So the idea of generative model is to try to reverse this notion of prediction we use in many applications. For instance, in the computer vision application I showed you earlier, the idea was if you have an image of a dog, it should be able to recognize that it's a dog, right? Whereas in the generation, it's the opposite, because I tell you, give me a picture of a dog. And that's where you should be able to recognize that there are so many different pictures of dogs you can put and learn this overall distribution, right? So learn to generate a good picture of a dog. And this is much more challenging, right? Because, here we are going from this large number of pixels to a few categories. So you have this dimensionality reduction. Whereas here, I'm just telling you it's a dog. If I'm not telling you anything else, you have to be able to generate this picture very well and also give you different options, right? You want different options of what a dog is. And that's why this is so challenging. And that's why we've seen a lot of really exciting development in the last few years. So let's do an exercise now. I call this the Turing test for faces. The last few years, we've gotten to generating highly photorealistic, high-resolution face images. In fact, I think recently there was even a launch of a catalog of people who don't exist. Like you can go and take these pictures of these fake people and use that in your marketing or something, right? So there's all kinds of ethical issues with that. That's something to be decided. But it has gotten to a really good place. And so I want you to do this exercise. Which one do you think is a real human and which one do you think was generated by an AI? How many think that the woman is real? How many think the man is real? Why? So, yes, indeed, like this one, and especially, I would look at the background here, right? So, the AI still has a lot of challenges with the background, and that's because, it kind of been fuzzy or because it's trained on so many different backgrounds. And indeed, like the expression and all that is still realistic, but, if I didn't show you side by side, you would think this is still possibly a human, right? I mean, a real human. So it has gotten to this really impressive quality just in a matter of last few years. And there's a lot of papers coming out of NVIDIA research on how to do this using progressive GANs and style GANs. GAN stands for generative adversarial models. And the idea is by looking at large data sets of real human faces, you can now learn to generate new ones in many different ways. And so this opens up a lot of directions in being able to generate very realistic looking models without having to do explicit simulation or go program the simulations. So now I have another interesting application I want to show you. This is known as GoGAN. You can go online and try this yourself. We'll just do a quick exercise here. Okay, so yeah. So the idea is, everybody can be now an artist, right? So I tried to be when I was a kid. I wasn't great at it, but now let's see how I do this. So there are many different scenes you can select. Let's select this one, for instance. So, I have ocean, I have some water. Now I can go and draw different things here. For instance, maybe I want some clouds. Let's do some clouds, right? So again, you can see I'm not a great artist. So let's see what happens here. So you can see that you can quickly visualize many different kinds of, right, like possibilities. So let's see what it does here. So I encourage you to go try this out. It's been, I think, used more than 500,000 times, and probably more since I last checked. So the idea is, again, this is a human-AI collaboration, right? The human can specify some parts of it. The AI can fill in the gaps. And in many applications, this can be so important because the human has good intuitions about what the image should look like or what should be in the image, and the AI can fill in the gaps. Let me get to the cursor, yeah. Yeah, so that's the GoGAN. And we have what's known as Omniverse, which is the platform for all these different rendering and different tools. And so, if you're a graphics artist, if you're an animator, you can use this. You can use Maya and Unity and all the standard frameworks. But also, if you're in roboticists and you want different kind of physics simulations, Physics and Flex are these GPU accelerated high fidelity simulators. And we can also bring this in. And if we now add in the power of generative modeling, there's a lot of very interesting kinds of generation and simulation we can do. And with that, we can build in embodied intelligence in many different ways. So again, Omniverse is something that can bring all this together and make it accelerated on GPUs. Yeah, so that's kind of the overall idea for embodied intelligence. What I tried to cover was how we want to think about the Trinity equation for these next generation applications. If you think about data, now it's highly multimodal data. You can have video, you can have speech, text, sensors, all these different modalities coming in together. How do we represent and process this? And that's where I describe the notion of tensors, which you can use to represent and build these tensor computations into the layers of neural network. And with this, you can get much more compressed networks as well as good efficiency with that. And with algorithms, the idea is you can augment deep learning with physics and other prior knowledge. You can do simulations at scale and bring them to the real world. You can use generative models like GANs and bring in generative modeling to augment predictive models like neural networks. And then we have the compute infrastructure. The AGX platform enables onboard computation at scale and be able to do, video and all these rich media processing. And so there's lots of interesting connections between these three facets that enable embodied intelligence. Thank you.
Are there any questions from the audience?
Hi. I just want your view on, I think it's the last one. So how do you think deepfake will really shape the cybersecurity domain in terms of face and voice recognition? Because this is what pretty much we say that this is the most secure way of authentication, right? but deepfake is really, something that just circumvent all these kind of stuff. So what do you think in this way?
Right, that's a great question. And inevitably, as these models get more and more realistic, right, deepfakes is an issue. And to this, I think, you can say, okay, we can also build AI systems to try to recognize what's fake and what's real, right? But I think there's a much simpler solution to this if different companies and platforms can agree on being able to have certificates and which can recognize what a real image is. For instance, we can go with the phone manufacturers, and if they can have like a watermark for all images taken on the phone, and then let's say software like Adobe Photoshop, maintains what was the changes made to the images, and platforms like Facebook and others, look at these watermarks and kind of keep track of that. I think there's a lot that can be done to handle this. So there's fairly low-tech solutions if we can get different companies to agree, but there's also high-tech solutions.
Any other questions? Then we will move to the Slidos.
Do I just go one by one, or?
Whatever you want.
Okay. So any misuses or bad uses of AI, right? So, the deepfakes is not at here mostly, but it's one that could come up. But also there is, I think the issue of bias and lack of fairness in many of the AI systems is probably the most important one, because especially AI is not regulated in most parts of the world. And if you now have applications like face recognition being used by law enforcement, and if there aren't enough examples of minorities who are also historically targeted, that can lead to potentially even dangerous situations, right? So we have to be mindful of what are the biases based on all this historic data we have, or imbalance in data, and have ways to test and be able to have enough regulation based on what is the impact of this AI being launched into the real world. Same with healthcare. I think I tweeted about this. There was a commercially approved skin cancer detection. So you could take pictures and, the app would tell you whether it was potentially cancerous or not. And it turns out that the data set they trained on had like a purple marker for all the cancerous ones. So, that should have been a simple thing to check. But, this app made it all the way to the real world, right? So it's something to keep in mind. How do we test all these different applications that are going to be launched, and who are the stakeholders, who will it impact, and how do we assess if there is a wrong decision, what are even ways to get around that? I think that's, to me, the most important set of questions. So the second one, in terms of the advances of algorithms being at the same pace as data and processing speed, I agree. The algorithms have mostly been around for a long time, probably even since the 50s or 60s, right? And with some important tweaks to make that work. But that's why the next generation of algorithms is what's exciting to me. Because just the brute force, take in data and do simple back propagation, I don't think will work for these new set of challenges I outlined. And more sophisticated algorithms will come into use. And that's what makes me excited as a researcher in AI algorithms. I guess that was similar, right? So, understand how better performance, how well do you think we'll be able to? I guess this question is about, if you've launched an AI system, can somebody else reverse engineer and reason about what the system is doing? right? So it depends on, again, what the application is. Is this somebody who wants to attack and do harmful things to a system being run by AI? Or is it a government regulatory agency who would have white box access, meaning they would have the complete model available and want to test that? So there's so many different use cases for why you would want to reverse engineer an AI algorithm. And I think there's a lot of now interesting research directions in terms of trying to reason about causality, right? So why is this AI algorithm making a particular decision? I mean, there is this famous, historic example, but also based on the skin cancer detection example I showed you, it was using a spurious correlation, right? It was using a marker that had nothing to do with cancer, but because it was in the data set, it was picking that up. So now if you want to reverse engineer and test, can you ask, why are you making this decision? And if you can pinpoint that through various metrics, then you can pick out those bugs. So it's very important to think of different ways to reverse engineer, but it's not trivial, right? Because these models are extremely big, so you can't use a simple model or an algorithm to try to reverse engineer that. So this area of interpretability and explainability deals with it, but I believe we are still in its infancy, and that's why, again, a lot of algorithms research will see interesting output in the next few years. So for the next one on AI algorithms being implemented on Mars rover, I mean, it's more traditional, path planning and control, right? So I wouldn't call it the modern AI. And that's where, if you go to like NASA missions, there's a very high bar for an algorithm to make it. And you also need to do it with extremely limited computational requirements. And so it would take still, I would say, quite a while for some of the latest algorithms to make it there. But that's an exciting challenge. AI advancing itself, I guess this is related to the question of singularity. Will we get to AGI, and nobody has to do any work, and all the world's problems will be solved, right? So I would say that's a utopian view. I mean, to me, sure, we can dream about it, but we are nowhere close to this, right? There are just so many different steps to go through before going anywhere near the ultimate part of it. But on the other hand, like, you could ask like an immediate question of, can AI help program better, right? Or pick out bugs, or help the human programmer make it faster, or help like a mathematician prove theorems in a faster way. And that's where there's a lot of interesting work. But again, we're very much in its infancy. But that would be the path to take. And there's a lot of exciting questions on, can AI come up with extrapolation? So we are not just interpolating like we are doing with the neural networks. Can it go and extrapolate and make new discoveries and decisions? And, there's some preliminary work that shows a lot of promise, but there's a lot to be done to scale that up and taken to real applications. I'm not sure what that means. Maybe we can go to the next one. So about the GoGAN, the next one. So the GoGAN is now a demo. Again, there is a lot of, the algorithms that I've gotten behind that, right? And like I described, that can have so many different potential applications. And so the goal is ultimately to combine that with the different forms of rendering and simulations, and add AI being also able to generate and augment that process. So that's the ultimate goal, but it's also available freely. So if you want to, use the demo, it's available online. I think we already addressed the attacks. So, thank you.
Thank you.